Okay, Assalamualaikum and good evening, everyone. Um, Before we continue our lesson, I would like to remind you about the test one. The test one, which will be held on 2nd of December. Okay, 2nd of December, uh, online. Okay, and will be conducted around 7:45 p.m. Okay. We send a reminder to the group. Okay, right. Uh, okay, so we stop somewhere here on the exercise. Today I would like to solve the example because I expect that you have tried it yourself, and then if you have any problem or don't understand to solve, you can ask me uh, later or anytime in the basically in the other means like WhatsApp. Okay. Also, this I skip. I just want to continue the precaution regarding using emitter. So remember that always connect an emitter in series of the circuit that we want to measure the current. Okay. So basically, if you have a circuit, okay, any circuit, okay, and want to calculate the current, need to connect an emitter in series. Okay, so always in series and always start with the highest range. Okay, as a very important precaution. If you start at the lowest, okay, if you start at the lowest, okay, uh, it might the deflection might be exceeding the limit. Okay, that it could go all the way to the right and hit the inner wall of the emitter. So you don't want that to happen. So the components are very fragile. Always de-energize the circuit before connecting or disconnecting the emitter. So how you de-energize? Okay, you short touch the positive and negative probe together. Okay, the probe was negative, touch it together. Never use a DC emitter as an AC current to measure AC current. Okay, because okay, it will create the oscillation. Okay, and also observe the polarity. Okay, so you need to know the direction of the current and and then the uh, positive, okay, will only oppose the uh, current direction, then negative to the ground, okay, negative to the ground. So you need to observe that. Otherwise, the direction will be the other way around. The direction of the uh, deflection. Okay, so it will create a unnecessary damage. Okay. Okay, insertion effect. So if you remember, for voltmeter, we have loading effect. Okay, but an ammeter, we have a condition we call as ammeter insertion effect. Okay, so this is basically, okay, uh, when the internal resistance, okay, uh, the internal resistance of the uh, ammeter basically, uh, internal resistance of the emitter basically become a part of the circuit that you want to measure. Okay, so in ideally, let's say we have a circuit with uh, B in supply, and then is connected in series with a resistor R. So ideal in calculation, we know that the current I is V in over VR. Okay, but when we connect an emitter, okay, basically is connected in series. Okay, but an emitter is basically consists of a PMMC connected in parallel with a shunt, okay, shunt resistor. Okay, so the total resistance, internal resistance of an emitter is basically R shunt in parallel with RG. RG is the internal resistance of the PMMC. R shunt is the shunt resistor. Okay, so the equivalent, this is the internal resistance. Okay, so when we connect the emitter in series, so the effective resistance of the whole circuit will be R plus the equivalent internal resistance of the emitter. Okay, so if in this case, okay, if the internal resistance is high, if this internal resistance is high, so current will decreases. Okay, that's why for an emitter, the internal resistance must be kept low. Okay, must be kept low. Okay, otherwise it will introduce as a significant value to the total resistance value to the circuit that you want to measure the current. So that's the case of an emitter. Okay, I hope that is clear. Now we come to resistance measurement technique. Okay, so we have covered the okay, and then we have covered emitter. So basically both the modification of the unsolvable device or the permanent magnet moving coil, okay, device. Okay, so we know that resistance, okay, from the Ohm's law. So basically resistance can be calculated if we can measure voltage and also we can measure current. Okay, so the technique that they can be used to measure resistance, okay, by using a combination of voltmeter and meter. Okay, by using an ohmmeter. The ohmmeter, we will see how PMMC can be modified, okay, to measure ohmmeter. Okay. But for an ohmmeter, okay, we will require external power supply to supply in the construction of the ohmmeter. Okay. Then also we can use Wheaton bridge. Okay. Uh, this is going to be covered in the next chapter, subchapter. Okay. And also we have a derivation of Wheaton bridge called as Kelvin bridge. So basically, Kelvin bridge is to measure low resistance. Okay. It is usually used to measure low resistance value. Okay. Okay, so now look at this technique using a combination of voltmeter and meter. Okay, so okay, in this example where we can use the combination of voltmeter and ammeter. So, but we have to follow the basic principle of voltmeter and ammeter connections. Okay. So basically, uh, the voltmeter will be always in parallel respective to the resistor. Okay. If we check the position of voltmeter, it must always be in a parallel position. Okay. But it must not be in series. Okay. And also we can use for ammeter, we put in series with the resistor that we want to measure the resistance value. Then we use Ohm's law, okay, R equivalent to V over I to obtain the resistance value. Okay, these are the two, as you can see here at the bottom. Okay, there are two ways how to connect the voltmeter, the combination of voltmeter and meter to measure resistance. Okay, for an example, the first connection, okay, we put voltmeter in parallel with the resistance, okay, with nothing in between them, okay, nothing between them. Okay, so that in this example, basically we want to measure R. When we put parallel in the resistor, basically it measure the voltage drop here. Okay. And then the ammeter must always be in series. Then we put sorry, correct. Okay, we put if you look at the example, seems current that coming from here. I need to rearrange everything. It seems like current is positive, negative, positive, negative. Okay. So then the meter basically will measure the I from the main source, okay, I is equivalent to IV plus IR. Okay, so in this first configuration we assume that IV is significantly low. IV is significantly low and equivalent to 0. Okay, and where I is equivalent to IR, or current that flow through the resistance, then we can use when we get the value of current from the ammeter, and then the value of voltage from the voltmeter, we can calculate the equivalent resistance. In the second technique, okay, we place the ammeter to measure the current that flow through the resistor R. In other words, in the second configuration, we put the ammeter in between the voltmeter and resistor. Okay. So in this case, we assume that RA, or the internal resistance of the ammeter, is close to 0, is very low internal resistance. Okay. So that we will not affect the current that flow through the resistor. We want to measure the resistance value. Okay, and then voltage is basically, okay, relatively in parallel with the resistor. Okay, and the resistor that we want to measure the resistance. Okay, so since RA is very small, okay, so VA, okay, is equivalent to I multiplied with RA. So basically VA is significantly low, so does not have any influence to, we will assume that it does not have any influence on the voltage measurement. Okay. So this is the first case configuration, IV plus IR. Okay. So R is from this R, okay, is from V over I minus V over RV. Okay. So in this case, if the internal resistance, ideal resistance or internal resistance of V is big, okay, so this term, okay, if RP is large, so V over RV is close to 0, okay, close to 0 amperes, therefore R will go V over I. Okay, so it must fulfill this, okay. RV must be very large and RA must be very small. Okay. In this case, R is equivalent to V over I minus RA. Okay. So to get the reading, okay, that is close to the actual value of R, in this case, RA must be very small. Okay, but of course, RV must also be kept at large value. So in summary, either resistance measurement technique, both must fulfill these two conditions, two condition of an ideal emitter and also an ideal voltmeter. Okay. Okay, let's look at this example, a voltmeter with 600 resistance and milliamp of Comparison the solution. Second, okay, so a voltmeter of 600 ohm resistance. Okay. Voltmeter with voltmeter R internal resistance P 600 ohm. Okay. Voltmeter and a milliamp of 0.8 milliampere. Internal resistance R I equal to 0.8 ohm. Okay. To measure two unknown resistance by using voltmeter and meter method. If the voltmeter reads 440 volt and the meter reads 100 in both cases, calculate the potential area in the value of measured resistance. Okay. In both cases, two unknown resistance, R1, Rx, R. Okay. In the first case, if the voltmeter is put across the resistor and the milliamp connected in series with the supply. So in the first case, the voltmeter is cross resistance and the milliamp connected in series with the supply. Okay. Here the ammeter, similar to the first condition lah. And this is the Rx. Let's say the Rx1, we don't know. Okay. But it says that in both cases, the reading is 40 volt for voltmeter and the milliamp is 100 milliamp respectively. Okay. So this reading will be 40 volts. Okay. And this reading is I here. I here will be 120 milliamp. But we don't know what is Rx. Okay. For the first case, this is the equation R in this case Rx1 equivalent to V over R sorry, I minus V over RV. Okay. I minus V over the resistance I and V. Okay. Okay. Rx1. So by using the voltmeter ammeter, so this is basically the calculate value Rx1. V is the 40 over 120 milli minus 40 over the internal resistance of the voltmeter is okay. So let's measure the minus 0.2 basically 40 over 0.053 153 milliamp. That's supposed to be 750. 700 is it correct? 750 ohm. Okay, got 0.0 754.72 ohm. That is with the internal resistance. Okay, so ideal in the first case, okay, when we consider this voltage, we divide by the total current. So 40, or we just consider this part, without the effect of the resistance of the voltmeter. Okay. So we see that an ideal 40 over 120 milli, so ideal Rx ideal 40 by 0.12, you get what's that? 333 0.3 ohm. Okay, so the percentage error, let's calculate. So the error it will be R X ideal minus, or it should be that, it's okay, we just put the absolute value R Rx1 from the calculation, from the measurement, divided by R X ideal multiply with 100. Okay, so you get a minus 754.72 right by 3.33. Okay, so you get what, 126.4% of error. Okay, is it? You see, it's a large, very large error here. Okay, because you see, immediately we can see that, you know, in this case, the internal resistance in this configuration, the internal resistance of the voltmeter, okay, affect, okay, the measurement. It affect the measurement. Okay, but for the second case, okay, the second case is the voltmeter is connected in supply side and meter connected directly in the resistor. okay, where here in the second condition, okay, where we assume this is 60 volt, right? 40 volt or 60 volt? Sorry, 40 volt. Okay, 40 volt here, and this is 120 milliampere. Internal resistance here we assume to be 600 ohm. This one is 0.8 ohm. So if we follow this, follow this R in Rx by using the voltmeter and ammeter device. It's of 40 over 100 milli minus 0.8. So this is 333.3 minus 0.8. It is around 332.53 ohm. Okay, but in this case, in this case, uh, okay, the ideal value, okay, we need to calculate the ideal value without, okay, okay, assuming that is the condition. So the I here supposed to be I supposed to be 40 divided by 600 plus 120 millivolt. That is what, 40 divided by 600 plus 0.12, 0.18, 0.18 ampere. So our ideal will be 40 divided by 0.18, two 0.22 ohm. Okay, so we calculate the percentage error. Okay, 2.22 minus 332.53, okay, absolute divide by 2.22 rho. So the error around 50%. Okay, so we can see using the second technique, assuming in the second technique here is the error here is 50%, and the first one the error is large, very large, 126.6%. Okay, so we can conclude that the second configuration the error is lower as the first one, but however 50% is actually large. Okay. Okay, large. Why in this case? Why it is large error? Okay, because you see at for the every both configuration to get the accurate result, the ammeter must be small and also the voltmeter internal resistance must be large. Seems the same thing for the second technique. Okay, the ammeter resistance must be small and the voltmeter must be large. Okay, but in this equation, okay, ammeter here, okay lah. This is fair. Okay, because basically good good. Okay, because the is low. Okay, low 0.8 the internal resistance. But for voltmeter here, this is we'll say is fair. For a good voltmeter, okay, it should have like 1 mega ohm, okay, or 100 kilo ohm, okay, in that range. The 600 ohm is low, okay. So in both cases, okay, there will be error, but in the first case, the error is significantly large. You see double, even more than twice or the actual value or the estimated resistance. Okay. Okay, so there's another technique. It's called using an ohmmeter. Okay, they measure resistance by using a power supply by providing a small battery to apply a voltage to a resistor. And then we use the Galvano meter. Okay. So first, this is the basic configuration. Okay, basic configuration of the ohmmeter, where it consists of a power supply V. Okay, okay, and then the meter is here shown. Okay, and then connected in series with the RO. RO is the an adjustable resistor. Okay, the purpose is to calibrate. Okay, to calibrate the ohmmeter. Okay, so basically this here is Galvano meter or the also device. Okay, this is basically just PMMC, the also device or PMMC. Okay, but the same thing like a PMMC, the significant thing about this is the label on the display. Okay, the label. So it show here the symbol. Okay, and then the needle okay, on a scale here. If you look at the scale, when there is no connection between A and B, okay, it means that the ohmmeter is open circuit. Okay, open circuit or no deflection. So when there is open circuit, means that here the scale here, okay, the value is infinity ohm. Infinity means it's large, very large, like an open space or vacuum. Okay, there is a number or value of the resistance of an open air, but uh, there is no significant reason why we need to put a value, but we just represent that as infinity. It's very large. Okay. Then RO, the purpose is to calibrate. Okay, calibrate. So how do we do the calibration? Is by short circuit this A and B. When we short circuit, means that here the value Rx is equivalent to 0 ohm. short circuit. Short circuit means there is zero resistance. Okay, so when we short circuit, okay, it should show a full scale deflection. Okay, from this IFSD equivalent to V over Rm plus R. Rm is the internal resistance of the PMMC. Okay, PMMC, and Ro is the resistance value of this adjustable resistor. So then when it deflect, we adjust so that the needle shows 0 ohm, 0 ohm here. Okay, 0 ohm. Okay, so which equivalent to the value of the resistance when we short circuit. Okay, short circuit. Okay, remember that when you short circuit, Rx or the value of Rx is equivalent to 0. Okay, so when there is no current I, no deflection, the equivalent value of resistance is infinity. When we short circuit, resistance is 0. Okay, 0. Then when we put or connect a resistor with a certain value that we don't know or we want to measure, so the current here I will be equivalent to Rm plus Ro plus Rx, which is equivalent to Rx. Okay. So before we continue, we need to put the range. Okay, put the scale value. Okay, what is the range of resistance at the scale? Okay, so that is done by calibration. Okay, so if we let P represent the ratio of current to the full scale deflection, we can say that, and this is the ratio P I equivalent IFSD. I is from here. I is from here. Okay. Oops. So I is basically V over V over Rm plus Ro plus Ro plus Rx. Okay. IFSD is basically V over Rm plus Ro. Okay. So if we take that as the ratio P, we get this expression. Okay. Get this expression. Okay. So this we get this expression. Okay. So this is the practical ohmmeter with a power supply of 1.5 volt. Okay, this is PMM IFSD. This is the internal resistance value of the PMMC. Okay, this is the adjustable resistor, and this is another resistor to limit the current. And this is XY that we want to measure the unknown value. So P is given by this term. Okay. So this similar with what I have explained. Okay. So basically, when we short circuit here, so when you short circuit, basically this is let's say this is terminal that we want to measure here. So this is where we put the unknown resistor. So when we short circuit, basically here RAB is equivalent to 0 ohm. Okay, when this is 0 ohm, we expect that the current that flow will be full scale deflection. Okay, full scale deflection, and here we set at 0 ohm. Okay, then we adjust here because it may be here, okay, over the scale when we short circuit, so we need to adjust, okay, by increasing or decreasing the value of here RO here, okay, RO, and so we have to find out lah. Sometimes it may start here on the left or maybe over the scale, so we adjust until we get the condition 0 ohm. When we open here, to mean that there is no current, I equivalent to 0, no current flowing through the MMC, no deflection. Okay, so no deflection, the needle return to its original position. So this is we label as infinity or infinity ohm. Okay. Okay. I'll leave this to you to read. We go to this example. Okay. Basically, 1 milliamp per scale deflection current is used to measure an Ohmmeter circuit. Okay, the meter movement has an internal resistance of 100 ohm, and the meter will be used to in the circuit mark the meter phase for reading. Okay, you mark the meter reading. Okay, based on 0.20, 400, 500, and 600 75 deflection. Okay, so the thing is that the circuit is something like this, 3 volt. So this is your ohmmeter or Galvano meter. This is the RG, internal resistance. So you can see RM. Okay. This is the RO, the adjustable resistor. Okay, and here is the AB. Okay, when we can put a value of X. So the thing is that we want to know, okay, so in this case we want to know what is the value when the deflection is at 20%, 40%, 50%, and 70%. 75%, if I'm not mistaken. Okay, 20%, 40%, 50%. Okay, so this is basically zero deflection, 0%. This is basically 100%. Okay. This is basically deflection 50%. Okay. This is roughly 20, 40, 20 maybe here, 40 maybe here. Okay, this is 20%, 40%, okay, and 75%. Roughly, we want to know what is the value in those deflection. Here, of course, immediately you know that this is infinity lah, infinity. So what is the value of 100% and so on? Okay. So we can use this the what is called as the ratio. You remember the ratio here, the ratio. You can use this formula. Okay, but you know we just need to find what is the Rx value. Okay, this is the ratio. Okay. So if you look, we, we get that the ratio P, the equation is P equivalent to R, okay, Rg plus Ro over Rg plus Ro plus Rx. So basically, these are Rx value at different deflection. Okay? So we need to know, okay, this is the percentage. Okay, P is the equivalent deflection. Okay, and then we want to know what is the Rx. Okay, Rx value. Okay. So at 0, P ratio is 0. Rx, if we put 0 here, okay, Rg, we know what is value Rg. The Rg is 100 plus Ro. Is it having this? Ro has been resistant. Oh, wait. Oh, in this case, Ro is Rz. Okay. So first we need to you need to know what is this is basically Rz. Okay, so need to know what is the value of Rz. Rz is when you short circuit here. Rx is value to 0. Okay, so when this is short circuit, okay, when Rx is equal to 0, so Ro or Rz is 2.9 K. Okay, fixed value 2.9 K. So here is 2.9 K over 100 plus 2.9 K plus Rx. Okay, so if you figure out what is the value of Rx, in this case, Rx is equivalent to infinity. Okay, so Rx here or Rg is 2.9. Okay, 2.9 K. Okay, how about when the 20% deflection? 20% deflection. So the ratio is okay. Is equivalent divided by 100 lah. Okay, so ratio here is 0.2. Okay, 0.2. Rx, okay, remain the same, 2.9 K. Of course, this is the zeroing value when calibrate. Okay. No, sorry, this is Rz. Sorry. This is Rx. Sorry. Okay. So this is supposed to be infinity. Okay. This is Rz. This is infinity. Okay. So now we find 0.2. So using this formula, so 0.2 equivalent to Rg plus Ro. So Rg is 100, okay, plus Ro, okay. So Ro is equivalent to Rz lah. which is actually this is the RZ. Okay, K plus 2.9 K over 2.9 K plus 100 plus Rx. If we figure out Rx value, it's supposed to be 12K. 12K. Okay, so here Rx is 12K. Okay, so here the value on the scale here is supposed to be 12K. Okay, yes. Here 100%, I think is when the ratio is what, 100% or 0 ohm. Okay. 0 ohm. Okay, no problem. 0. Okay. But I think you can try for 40%, 0.2. RZ will be the same. So in my calculation here for 40% or ratio of 0.4 is supposed to be 4.5. Okay. Okay. 50 0.4 0.5 is 2.9K. For 50% Rx should be 3K. Okay. As for 75%, 0.75, 2.9K, this is supposed to be 1K, 1 kilo ohm. Okay. So that's the answer. Okay. For you can see this is the answer. You verify. Is it? Okay. Yeah. Right. I think we stop here. Okay. Stop here and then we will continue this Sunday. Okay. Thank you for your time. Assalamualaikum warahmatullahi wabarakatuh.